So welcome back after a long weekend away, although it may not feel like you were away on Friday. You were. And we're on schedule, continuing according to the syllabus with a little section on cell membranes, and there's a reason for doing this part here and now when it is in the course, because this is a combination of protein and lipid and carbohydrate. This one structure is a way of doing a brief review of the three major kind of biomolecules that we've looked at so far, and it's also pretty handy to be thinking about how all of them fit together and work together. I left some space here now. I know that there are plenty of diagrams of cell membranes out there. There are a dime a dozen. But let's try to put this together in a way that kind of gives you some motion on it and also emphasizes the categories that we've talked about so far. So I think I mentioned earlier what the lipids look like. Let's just line up a few of them. They have tails that look like this. I'm trying to keep these approximately to scale for the size of the molecule. That's not way off for whatever it is. And then tail to tail comes the other side of the membrane, looking like this. So there's the lipid, and it will have a portion to it that's lipophilic tails. This whole thing is going to be compared to like a hydrogen atom. This is on the large side, but this is going to be what we refer to as just the lipid bilayer. Now that's kind of component number one. You imagine this whole thing as a sandwich, and it's tail to tail, so that the head groups are on the outside. So that's the other organizing principle. Both top and bottom of this, you might envision a layer of water. This would be water inside the cell, whereas the other one is on the outside. Looking like that. Now, there's more than just lipids, fortunately, to the whole thing, because here's what you can imagine now, and I'm turning this sideways on purpose. We talked about how there are steroids, cholesterol specifically, and I'm going to draw most of the steroid. Okay, it looks like that. I may have drawn that a little bigger than it should be. That's okay. There's the OH, and it's most likely going to be pointed out, down inside the cell, or outside. Whatever it is, here's a zone where you've got cholesterol. And its job is to be there and stiffen. It stiffens the membrane. Now, keep in mind that what you're looking out at right here is actually two different categories of lipids. There's the kind that look like this, and there's the kind that looks like this. All of them lipid. They would dissolve in chloroform or hexane or whatever you wanted to throw at them. So meanwhile, the lipid continues on, the lipid layer continues on. It is mostly lipid. Okay, and the cholesterol probably has a zone where maybe its only partner above it is a lipid, and then the whole thing just continues like this. Okay, that steroid framework is a lot less flexible, less floppy than the tails of the lipids. Now, of course, you don't want to get into the habit of thinking there's only one cholesterol molecule in the membrane. This is just one zone. Then you come to another zone, and this is where we kind of unite with some of the other categories of molecules we've talked about, biomolecules. This thing is drawn as a big chunk on purpose because that's exactly what it is. this is a protein, and the way it's sketched here, it's an integral protein. Integral meaning that it's not just on the top or on the bottom. Now, those things do exist. Okay, might as well sketch that, I guess. Make yourself another blob looking something like this. This one's still a protein, but it's a peripheral protein. Okay, and there'd be some features worth noting on the protein. I don't know if you remember from the discussion of proteins themselves, but they tend to be arranged so that when they're wadded up, if they belong in a membrane, it's not just any old R group that sits right here. Now, the protein, of course, will be coated with this R group, so that these R groups that stick outside of it, and they're going to be definitely nonpolar ones, because that's what makes them compatible with the middle part of the membrane. They'd have their most polar R groups top and bottom as well. So they're designed so that they really do fit. It would also make sense while we're here to do something and try to keep this kind of small. Okay, compared to the protein, that little piece that I've displayed right there is going to be something else. So here's the proteins themselves are kind of biomolecule category number 2, lipid, protein, and then finally up here is a spot for carbohydrates. So carbohydrate on the outside, that's where they would sit. They would be covalently bound to a protein, and they sit there on the outside and kind of give the cells identity. I am a whatever it is, a type A or a type B. But you're not done, because the story continues. You have all these little lipid molecules, jillions of them, all looking pretty similar to each other, but they're not boring for that reason. You really do need them to hold the cell membrane all in one place. That's your 3 categories. So here's what you have. You have, let's see, I named lipids as number 1 and proteins as number 2, in this diagram, that is, and carbohydrates as number 3. All of them there. There are better, prettier diagrams of cell membranes out there, but if you've made this one and kind of know how the 3 components sit and what they do, that's the important thing for here. I guess it looks like I put a little bit of text with this as well. The lipid bilayer is the basis. Nonpolar interactions. Okay, so that means there's no hydrogen bonding. It's between the tails. It's all lipid-lipid interactions. Cholesterol sits there as well, strengthens things. Then we have proteins that do exactly what you would expect. It looks like I've got a little bit of extra space here where we could do a better job of representing these. I'm going to blow up that version of an integral protein that you saw in one spot. And let's put the R groups in a bigger view, looking something like that. Okay, the lipids look sort of like this. And so in this spot right here, you have hydrophobic interactions. As always, like dissolves like. In a sense, you have just a little puddle of oil, oily regions right in the middle of the membrane. Oil from the protein on its surface, oil from the lipid in its tail. They are compatible and they head for each other. So that's the way an integral protein stays in place. It has to stay in place. The peripheral ones are a little bit more loosey-goosey in the sense that they can move around. They're not as big, plus they're on the surface. But they are held in place when they are by the kinds of things that you would expect. So your peripheral proteins, some of them, the ones that are the most tied in place, would be held in place by ionic interactions. A few of them maybe by nonpolar interactions, although there's not much of that possible on the cell membrane. And on the hydrogen bonding side, yeah, probably some of these as well. So what you would envision is probably less of this because it is on the cell surface, and maybe more of this. For whatever reason, they are able to swim around on the surface, but still not escape the cell. Now, if they're so loosely held that they jump outside the cell, they don't do you any good anymore. That's not the idea. There's a whole category of peripheral proteins that have roles that will matter to us in this class later. They function as receptors or enzymes. Okay, so receptors, so they're going to bind to specific, very specific molecules, and in doing that, they're going to import them, or at least detect them. Enzymes, the proteins that look like this, if they're enzymes on the surface of the cell, they're going to carry out reactions right on the cell surface. And that's good because some things need to be broken down before they enter the cell. All right, then the other main component, the other main kind of biomolecule that is, that we're looking at all as part of this cell membrane picture is the carbohydrates. They're covalently linked to proteins, and we had a term for that earlier, which is we call the whole combination of glycoprotein. They sit there on the surface and help cells recognize each other. You put all this together, this diagram that we started with, and there's a term that goes along with it. So let's kind of elaborate on each one of these. You've seen the picture certainly in this class and in others. Fluid, I'm not sure that this is stressed in the biological realm, but from the molecular realm, here's what it amounts to. This membrane, as we've sketched it, is in motion. You can see movies of this. I think there's some on YouTube. What happens is that the molecules, this isn't a technical term, but use it anyway, they swim sideways. So it really is fluid. We draw it as just one thing, but everything is in constant motion. Mosaic. Now, that means several things. One is that it changes with time. The minute you draw it, or the minute you take an electron micrograph of it, you've seen only one version, and it's not what would exist 5 minutes later. Another thing about it is it's not all the same. You have zones that are rich in proteins. So something like protein-rich zones. You also have lipid zones. Oops. This reminds me of discussions of the gut biome. You heard that talk, intestinal biome, gut biome, in us humans. There's a debate about whether there's any such thing as an ideal gut biome. Consensus seems to be no. And the problem is, the minute you measure it, it has changed. Because it changes throughout the day, it changes in response to what you eat, and so forth. There's no one right answer. It's kind of the same with the cell membrane. It's kind of hard to pin down. You know what it is on average, and you can certainly measure their overall composition. They tend to be, what, maybe 60%, this is by weight, 60% lipid, 40% protein, but it depends on the organism and the cell and so forth. There's no one correct picture here. And so that means that movement through a membrane is similarly complicated, which is kind of cool. It means that it's easy for molecules that are small or nonpolar. So this is stuff like carbon dioxide and oxygen and water, the usual suspects for metabolism. And notice what they all have in common. They're not charged. They're not big. Now it's harder for molecules, and let's kind of say what we mean by larger molecules. Larger would be stuff like whole proteins. It's very difficult to get them in and out of a cell unless there's a specific gate for them and they are specifically welcomed. Okay, but just bumping up into a cell and hoping to get in by knocking your way through the membrane, not very likely if you're a protein. And that's a good thing, right? You don't want just any protein hopping in at any time of the day you want. There's kind of a rule here. Small could mean a molecular weight of less than or equal to about 600. And for a protein, that's tiny. That would be like 6 amino acids. Any larger protein big enough to be metabolically active, like an enzyme or a toxin or something like that, it's too big. So, and by the way, this number for 600 is kind of a cutoff for people who design drugs. Most drug designers will tell you if we're going to treat a condition, we better make sure we keep the molecular weight under 600. Otherwise, it's hard to get it inside of a cell. You might have to tag it onto a protein or tag it onto a special label so that the cell is more interested in it. But by the time you get above that, it's starting to slow down. I don't want to make too much of that number, but that's a borderline. Ions, it's harder for them, but there's a plan for them as well. And the most common ions that you need to be concerned with are obviously your electrolytes, sodium, potassium, and chloride. They get in and out relatively easy for ions, but as you probably know, they have to go through a protein that's specifically designed to be a gate for them. So let some of them in and some of them out. Neurotransmitters probably also fit in this category. Most of them have an amine group in them. So that's going to be charged at body pH. Most neurotransmitters are cations or anions. That's why they have the effect they do. They can depolarize a membrane really fast. Okay, so that's the consequence. All of this situation right here, easy for some, hard for others, all that falls out of what a cell membrane is. It's designed or evolved, depending on how you want to see it, so that all of this is true, and that's a good thing. It should work that way, and it does. All right, that's a little review of carbohydrates, proteins, and lipids, except combined as a cell membrane. Okay, so why don't we continue on, make a little bit of headway into this next category, and where are we time-wise? Let's take a break. You need to clear your head, take a drink, stand up, or something like that. Before we start this next piece, I'm going to try not to do it all in one sitting, because it does take some concentration. Were you hoping you were done with things like G's and H's and stuff like that? Not quite. Okay, how about if we start up again with the last leg today. Taking this a little bit out of order, but that's okay, it works. We're talking about something that you've seen before if you had freshman chemistry, and if you had organic, you probably had a little piece of this anyway. Free energy changes and standard state. So here's what matters for a biochem class. The free energy is something that determines if a reaction wants to happen. And the symbol we're going to use for that in G is G. Now, what you'll see more often, though, is what we care about is the change in G, and that has the usual symbol of delta. All right, so that's what we're talking about. It's the energy available to do useful work, as in not wasted. Trying to think of how to say this. What is wasted? You've heard of this term before, entropy, right? That's a waste. That is a total waste. Entropy is wasted energy. That won't be quizzed or anything, but you remember the symbol for that? S? We've seen that before. All right, here's the way we do it, and this starts looking pretty biochemistry-like in a big hurry right here. You're going to think of this as kind of a thought process, comparing delta G. This is how you think of change in energy. Okay, you don't necessarily have to have that written. All right, you're looking at a reaction. You assume you have at least one reactant and one product. On this side, you're envisioning something which is how much energy content. That's not anything that you'll measure directly. You're also asking the same question over here. And again, you don't measure it directly. Okay, so there's in here, right here in the middle, here's delta G. It goes up or it goes down. And so what I want to do to begin with is give you some words and some maybe different ways of saying the same thing to help you kind of connect to all this. If delta G or delta H is negative, what that's saying is we're using H as a proxy for G, and this is something that you can see. A decrease in G means that you'll see something about heat, and specifically, it's given off. If heat's given off, that's strong evidence to you that delta G is going down. It's negative. It feels warm to the touch. You tend to not given in your freshman and sophomore chemistry classes, you tend to not be given reactions that involve a lot of heat in a big hurry, and that's for safety reasons. You don't want something that takes off that fast. But if it is warm to the touch, that's evidence that you're in this territory right here. The reaction, you say, is spontaneous. And another way of thinking of that is it wants to happen on its own. That's a, quote, good reaction. You don't have to heat it or anything like that to make it happen. Now, in the category of work and whether or not it's useful or not, that connects to the whole definition of free energy. What can happen is a reaction like this can provide heat, for the body. We have to have heat in order to maintain the right temperature, not too hot, not too cold. So you need a spontaneous reaction for that to happen. another main use for decrease in delta G is to create new compounds. So this would be something like ATP, which is the energy currency of the cell. You've probably heard it referred to as that way. ATP is made because there's not just one reaction, a whole set of them that all taken together are spontaneous, and you put them like in a little machine and force them to make ATP. That's one thing that happens. Here's the other way that a change in G can happen. If it's positive, this is probably the most easily confused part of it. It's going to feel cold to the touch. It soaks up energy. It's safer to give people in freshman chemistry this kind of reaction. So for instance, just dissolving some inorganic compounds in water will make the solution feel cold. Did any of you have any like that you remember? Did they, in freshman chem, did they ask you to mix up any solutions and you touched it and it felt cold? That happens. My sense is that table sugar is a little bit like that. Maybe try that. Dump table sugar in water. If you do a lot of it, so that you can tell what happened thermally, my memory is it gets a little bit cold. It's sure not exothermic. Okay. Another way to say that is that the reaction is not spontaneous. And here's the main caution. So I'm going to switch colors for this. It doesn't mean impossible. It just means that it's going to need some help in order for it to happen. Right in the middle of the citric acid cycle, which is one of the main cycles for degrading glucose and getting biologically useful ATP out of it, there's this one reaction that has a delta G that makes everybody look at it and go, why? Why should this even be happening at all? It looks like it shouldn't. Well, that's because even though it's not spontaneous, it's still not impossible. It is driven by other reactions around it. It has to have help. That's all it means. You can do work to make it happen, and here's how that works. By using other reactions to drive it. So your car doesn't want to roll uphill all on its own. Known, accepted, no problem. You can still get your car to go uphill, it's just you have to help it. You have to push it. One way to happen is to use other reactions. Another way to do it is by heating it. Sometimes that's all the trick you need. Okay, now that's the whole thing without numbers. That's what delta G looks like when you just think of it. But you'll need to be able to interpret some numbers. Now, again, don't think of memorizing formula here. This is how to use formulas that are given to you and how to interpret numbers that come to you. So you're going to assume a reaction, and I'll even put an example on it. So let's say glucose, and here will be some other reactant. And let's say that when you're all done, you have some glucose derivative. Something stuck on one of the oxygens, something knocked off the ring. And now you have some leftover molecule. And you put those two together, two reactants together, allow them to combine, and then you're looking at a calculation that will allow you to say something about this reaction. Here's what we're going to look to define about reactions like this. The calculation we're going to be concerned with is a change. So delta G a change, delta G. That's what we're looking at, and it will tell us if this reaction is spontaneous, yes or no. Right, that's the interpretation we'll be looking at. And there's a calculation using a formula here that you don't have to memorize, but let's be able to interpret. So delta G, which is what we care about here, is calculated using a starting point, delta G 0. This is kind of your home base. This value right here, it's delta G specifically when the reaction is at equilibrium. So you have let it happen, and then you've measured to see how much energy got evolved. So that's one thing to be aware of. It's at equilibrium. Also, it's going to be calculated with all concentrations at one value, and that one value is 1 molar. You got to start somewhere, and this is where you start. So every reaction can be kind of ranked like this. Take any two reactants that are known to like each other, throw them together, equilibrate everything, let the reaction come to where it's in equilibrium, make sure all concentrations are 1 molar, and you've got yourself this one number, and only this one number. But in real life, that's not where most biological reactions happen. Okay? They happen somewhere off the map from where the standard value is, so you adjust. And here's an adjustment which we're going to ignore by saying it's a constant. You can calculate that. And then up top here, in this part of the reaction is one thing to talk about, and as well as one in the bottom. All of these up here are products. Reactants go down on the bottom as usual. And here's what you're going to put for both of them. Their molar concentration. And keep in mind, in the real world, probably not 1 molar. 1 molar is where you start, just because you have to start somewhere. Okay, now the biological world is going to be at a special set of conditions: body pH, body temperature, the conditions that we care about, because we want to know what happens chemically under biological conditions. So here's how we would do this for biochemical reactions. This is a special version of that other formula, and it's more useful for what we care about. And here's the big thing that's different from the delta G of your freshman chemistry, and it's this. You don't worry about making all concentrations equal to 1 molar. Think of what that would be. If you had a hydrogen ion concentration of 1 molar, what would the pH be? Do that somewhere else. Well, you know the definition of pH, right? It's the minus log of this right here. What would be the minus base 10 log of this? 0. Right? A pH of 0. Do you know of any biological molecule that would survive a pH of 0? That's sulfuric acid. Okay? So that's why we have to come up with our own set of conditions. You let the pH be equal to 7. 1 molar, that would be dangerous if it were the hydrogen ion concentration. So that's why you pick a different hydrogen ion concentration, pH 7. So 10 to the minus 7, much more mild concentration. The pH 25C, that's a little bit below body temperature. Body temperature is 98.6 Fahrenheit, right? What is that Celsius? It's like 37, 38, something like that, Celsius. So this is a little bit below body temperature, but it's more or less room temperature. So it's a pretty realistic temperature to be measuring. And you use the same form of this equation right here. The difference is, this one right here is the new biological version of delta G0. It's the prime that makes the difference. Prime means biological conditions. Okay, I think we're kind of at a break point between sections. Yeah. It's a little bit early, but I think we'll just call it done right there. We're very easily on schedule. I don't want to break up the next piece of it. So let me compare where we are with the schedule. Yeah, we're very much on schedule. So we will probably end a bit early next time and have extra time for review for the exam. Is that on your radar? Is that on everybody's radar, next exam? Okay, we'll start review for that a little on the early side. See you Wednesday.